Hello everyone, this is Ghazi Hadiwad. I'm presenting Impala real-time query engine for final project in CSCI-E63 Big Data Analytics course at Harvard Extension School. On October 2010, Google published a white paper on Dremel project describing a distributed system developed for interactively querying large datasets and powers Google BigQuery services. Dremel is a scalable, interactive, ad hoc query system for analysis of read-only nested data. By combining multi-level execution trees and columnar data layout, it is capable of running aggregation queries over trillion rows tables in seconds. The Dremel white paper was the inspiration for the Cloudera team to bring real-time ad hoc query capability to Apache Hadoop, complementing traditional MapReduce batch processing. Before we drill deeper in the description of Impala and to understand Impala's position in the Hadoop ecosystem, it is necessary to give a brief description of the problems that are solved by Hadoop. The landscape of the database market is currently influenced by the use of relational databases, RDBMS, such as MS SQL, MySQL, and Oracle. RDBMS model is facing constraints that are limiting its use and application. These limits are scalability or volume and speed or velocity. The first constraint limits the size of data to the ranges of gigabytes or terabytes in some cases. The second limitation, speed, is not serving the current set of problems that businesses are faced with, where many are challenged with the need for real-time availability of data processing in a high velocity. With a deluge of information led by the use of Internet of Things, IoT, social networking, and behavioral data, to name few, these limitations are hindering the business ability. Although Hadoop is not a database by itself, it is an alternative data system with processing library and engines. As mentioned earlier, Hadoop is developed to overcome the limitations of RDBMS, to solve problem sets that cannot be solved by RDBMS. The following is a list of some of the techniques and approaches that are used in Hadoop to overcome the RDBMS limitations. 1. The use of massively parallel processing. 2. Use of alternative file system, SDFS. Use data partitioning and MapReduce, limiting transactional use, so there is no update and the data is immutable data. Bring in the code to the data instead of bringing the data to the code. So the code is not pulling from the database as the usual approach we're doing with the conventional RDBMS. No, the code is sent to the database as jar files. The use of wide columnar store, using schema on read instead of a schema on write, and other approaches. While relational databases use schema on write to express relationship between data points in a dense data storage as it is written. This data modeling approach, also called prescriptive data modeling, is good for repetition querying or finding unknown unknowns. Hadoop uses schema on read, also known as descriptive data modeling, where data is copied in its native format and schemas are created at reading time. The reason for this choice is to overcome the following downsides of schema on write. In a schema on write, schemas are typically purpose-built and hard to change. They require considerable modeling implementation effort before being able to work with the data. If a certain type of data cannot be confined in the schema, you cannot effectively store or use it. Unstructured and semi-structured data tend not to be a native fit. Although schema on read approach can be quite expensive because it depends on higher memory and that the data will lack self-documenting, The flexibility provided by using schema on read outweighs the use of schema on write for the following reasons. It gives you massive flexibility over how the data can be consumed, so you will have ETL on the fly. Your raw atomic data can be stored for reference and consumption years into the future. This approach promotes experimentation since the cost of getting it wrong is so low. It helps to speed the time for data generation to availability. Schema on read gives you flexibility to store structured, semi-structured, and or loosely or unorganized data. It allows for exploration, which is finding unknown unknowns.
The traditional Hadoop design consisted of two parts, HDFS and MapReduce. However, the introduction of YARN, resource management, the file system and storage are separated from MapReduce, and MapReduce became just one of the many applications of Hadoop ecosystem. Impala is part of Cloudera Hadoop distribution, CDH. The Cloudera Hadoop distribution has 5 main areas: storage, HDFS file system, HBase data storage, and Accumulo, which is a key value store based on Google Bigtable. Second, resource management, which is YARN and Llama, which mediates resource management between Cloudera, Impala, and Hadoop YARN. Third is metadata store. Both Hive and Impala share the same metastore database. For data movement and integration tools, Flume and Scoop to load and unload data between relational database and HDFS files. 5 libraries and application engines for batch processing like Hive and MapReduce, or interactive querying like Impala, or scripting like Pig, or interactive searching like Cloudera Search, streaming processing such as Spark Streaming, and machine learning Mahout and MLab. In this presentation, we are interested in 2 parts of this ecosystem: the batch processing, which Hive MapReduce, and the interactive querying engine Impala. Hadoop has several engines for data summarization, querying, and analysis. One of these engines is Hive. Hive Data Warehouse software facilitates querying and managing large datasets residing in distributed storage. Hive provides a mechanism to project structure into this data and query the data using SQL-like language called HiveQL. In CDH, you can use Hive or Cloudera Impala. The difference is that Hive is batch processing SQL-like query that produces MapReduce code to accomplish its tasks, while Cloudera Impala does not rely on MapReduce for query and completes its tasks in memory. Hive was originally developed for use at Facebook for those developers who knew SQL code and did not develop in Java. It is a set of libraries that uses HQL. HQL is a SQL-like language that generates MapReduce. The batch nature of Hive means that there will be latency in the results in comparison to what RDBMS SQL users are used to. Hive maps HDFS files to other objects that are familiar to databases users, such as database, roles, tables, columns, etc. As the data schema in Hadoop is not defined until the data is read, querying the data store for data requires parsing, formatting, and processing of the data. This cannot be done in conventional SQL language and requires code such as the one of MapReduce. Hive gives the convenience of SQL-like language, but through MapReduce batch jobs. The following are the components of Hive's shell or UI, which allows for interactive queries and connection to the database. Second is the driver, handles session, fetching, and other activities. There is a compiler where you'll see query parser, semantic analyzers, query planner, and query plan optimizer. Then there's the execution engine, where the execution of the compiled query plan happens. Then there's the metastore, provides storage information, data abstraction, and data discovery. Its objects are database, tables, and partition. The MapReduce approach of Hive is suitable for batch processing tasks. These tasks may take minutes, and some can take hours or days. This is not suitable for real-time analytics. Hence, on 2012, inspired by Google Dremel, Cloudera launched Cloudera Impala, a real-time query engine for Hadoop. Cloudera Impala provides fast, interactive SQL queries directly on your Apache Hadoop data stored in HDFS, HBase, or Amazon Simple Storage S3. In addition to using the same unified storage platform, Impala also uses the same metadata SQL syntax, the ODBC driver, and user interface, HUE, as Apache Hive. This provides a similar and unified platform for a real-time on batch-oriented queries. Different from Hive, Impala executes queries natively without translating them into MapReduce jobs. To avoid latency, Impala circumvents MapReduce to directly access the data on HDFS data nodes using local direct read. This provides the following benefits of Cloudera Impala. 1. Familiar SQL interfaces that data scientists and analysts already know. 2. The ability to interactively query data on big data in Apache Hadoop. 3. Distributed queries in a cluster environment for convenient scaling and to make use of the cost-effective commodity hardware. 4. The ability to share data files between different components with no copy or export-import step, for example, to write with Pig, transfer with Hive, and query with Impala. Last but not least is single system for big data processing and analytics, so customers can avoid costly modeling and ETL just for analytics. A Cloudera Impala solution is made of the Cloudera Impala server and other components of the Hadoop ecosystem. They are as follows. Client. Entities including HUE, ODBC client, JDBC client, and the other Impala shell can all interact with Impala. These interfaces are typically used to issue queries or complete administrative tasks such as connecting to Impala. Second, Hive Metastore, which stores information about the data available to Impala. For example, the Metastore lets Impala know what databases are available and what the